everyone, welcome to my channel Chemistry by ANR. Today's topic is hydrogen bonding. So this type of bonding is considered to be very strong bonding. It exists between H atom and with electronegative atom having small size and greater electronegativity. So not all atoms are considered to be able to form hydrogen bonding. They are atoms like oxygen, nitrogen and fluorine that are capable of forming hydrogen bonding. So hydrogen bonding can be of two types. One is intermolecular hydrogen bonding and the other is intramolecular hydrogen bonding. Intermolecular hydrogen bonding is the type of bonding that exists between molecules, one molecule to the other molecule, forming associated molecules, associated interaction, one molecule to the other molecule by association. So this type of bonding is considered to be very strong bonding, and the type of bonding that exists between the same molecule or the same structure is known as intramolecular hydrogen bonding. Maybe oxygen, fluorine or nitrogen atom is present in the structure of the molecule and there is H with the structure of the molecule. That can be this type. Suppose this is one type of molecule and the type of interaction develops between this atom to the other atom, or maybe between this atom to the other atom. So within the same structure, same molecule, the interaction, the hydrogen bonding is taking place. So that is known as intramolecular hydrogen bonding, as in O-nitrophenol, and intermolecular hydrogen bonding as in p-nitrophenol, or maybe between molecules of HF. If this is one molecule of HF, this is the other, they are held together by intermolecular hydrogen bonding, forming associated molecules. Compounds which form intermolecular hydrogen bonding, they have greater boiling point because of this associative interaction. So you need more energy to break these associations. So let us see in details. Hello everyone. Hydrogen bond is a special type of bond that exists between particles that can be in the liquid state or in the solid state, like in ammonia, water, hydrogen fluoride, ice, etc. So in all these cases, this type of special bond occurs, which is a dipole-dipole interaction. Actually, it is not a pure dipole-dipole interaction. It exists like a dipole-dipole interaction. That means the type of interaction that occurs between hydrogen atom and the other atoms like oxygen, fluorine and nitrogen, which is highly electronegative and is small in size. So the hydrogen atom which is there in a compound is covalently bonded, and the type of interaction that exists with the other atom are oxygen, fluorine or nitrogen on account of its small size and high electronegativity. So that is what is seen over here. Z is taken as in common, which can represent any of oxygen, nitrogen or fluorine. So here we can see HZ is one molecule. So the type of interaction that exists between the molecules HX is hydrogen bonding, and the type of interaction that is shown over here is intermolecular hydrogen bonding. It is intermolecular hydrogen bonding. So this is one molecule, this is the other molecule, type of interaction existing between delta negative Z and delta positive H is intermolecular hydrogen bonding. So it is type of electrostatic force of attraction existing between covalently bonded hydrogen atom to one molecule and electronegative atom of the other molecule. So this type of interaction is intermolecular. So there are other types as well, like intramolecular. So HF, hydrogen fluoride, HF, molecules are held together by intermolecular hydrogen bonding. Delta negative is the polarity developed over fluorine on account of its electronegativity, and delta positive is the polarity developed over hydrogen. So the type of interaction that exists between delta negative end of one HF entity to the delta positive end of another HF entity is known as intermolecular hydrogen bonding, and it is a very strong interaction amongst the type of all other interaction. But keep in mind, this is not as strong as a covalent bond, because covalent bond is a real bond formation and hydrogen bonding is not a real bond formation. It is a type of interaction on account of the structure of the molecule. So hydrogen bond is much weaker than the covalent bond, and its strength ranges from 12.5 kilojoule per mole to 41.5 kilojoule per mole. Next, conditions for hydrogen bonding. What are the conditions for hydrogen bonding? It exists as a dipole-dipole interaction because there is induced polarity. So it is like a dipole-dipole interaction. And what are the conditions for effective hydrogen bonding? Let us see. That is the electronegativity of the atom. As I said, oxygen, nitrogen or fluorine, they are highly electronegative, on account of which the strength of the hydrogen bond will vary as F greater than O greater than N. That is, HF hydrogen bond is a stronger than HO hydrogen bond existing in water molecules than HN hydrogen bond existing in ammonia molecules. Size of the electronegative atom. So electronegativity is one such point. Size of the electronegative atom is the other point. If the size of the electronegative atom is large, then its attractive force with hydrogen will be less. So for that reason, nitrogen and chlorine have same electronegativity, but no hydrogen bond exists between the molecules of H and Cl, whereas hydrogen bond exists between the molecules of H and N. So we can say that HF is hydrogen bonded. So like this, HF is hydrogen bonded, whereas HCl is not having that type of hydrogen bonding. So intermolecular hydrogen bonding is not existing in HCl molecules. So obviously it will affect its properties as well. So examples of hydrogen bonding are, we have seen in hydrogen fluoride, where fluorine is more electronegative, having a small size even. So the boiling point is expected to be higher, and the bond enthalpy should be higher. But bond enthalpy, we are not talking about the covalent bond. We are talking about the boiling point, where the energy required to break the interaction between molecules is accounted for. Water molecule. Water is extensively hydrogen bonded. We can see over here that oxygen atom is bonded to two hydrogen atom, and due to large electronegativity of oxygen atom, a negative center develops. So delta negative develops over oxygen, and to the next hydrogen, which is a delta positive, what will happen? There occurs a hydrogen bonding, and this type of hydrogen bonding is again intermolecular hydrogen bonding because it exists between molecules of H2O. Ammonia also, in ammonia we can see the type of hydrogen bonding that exists is intermolecular between delta negative of nitrogen and delta positive of hydrogen. So here we can see delta positive of hydrogen. This is the type of interaction that exists between NH3 molecules. Now, what is the influence of hydrogen bonding? I have said in the introduction part that the hydrogen bonding influences the boiling point also, and it causes what? Association of molecules. So, since it causes association of molecules, it will increase the boiling point of the molecules. So, HF is associated, and n number of HF can be held by hydrogen bond, which is known as intermolecular hydrogen bonding. Now the melting point and boiling point will be higher So let us compare the boiling point of hydrides of elements of group 15, 16, 17 in the periodic table. The hydrides of the first member of each group, like nitrogen, for group 15 nitrogen forming NH3, for group 16 oxygen forming H2O, for group 17 fluorine forming HF, they have abnormally high boiling point. For example, in case of halogen acids, haloacids, like HF, HCl, HI, HBr, here what is happening? The boiling point decreases with decrease in the molecular masses. That is from HI to HBr. Why? Because HI has more molecular mass. The relatively high boiling point of HF is due to the presence of intermolecular hydrogen bonding. If the molecular mass is increasing, then what happens is the van der Waals interaction increases. Hydrogen bonding becomes weaker. Okay, so next let us see. Similar explanation can be given to explain the abnormal boiling points of H2O among the hydrides of elements of the oxygen family than that of ammonia, NH3, among the hydrides of elements of the nitrogen family. So here we can see the boiling point of NH3 is high rather than PH3. Again, it increases in ASH3 and SBH3 because the molecular mass increases. Next, you can see HF is high. There is a decrease in HCl and gradual increase for HBr and HI because the molecular mass increases. Molecular mass increases, so van der Waals interaction increases. You need more energy to break those interaction. But we can see the extensive hydrogen bonding of HF, which is causing a greater value to the boiling point than HI also. Similarly, H2O, that is oxygen family, hydride of oxygen family, is having very high boiling point rather than H2S or H2SE or H2TE. So this is it. Now we can see that it affects the solubility as well. Boiling point and solubility are physical properties that are both affected by hydrogen bonding. Solubility of alcohols ROH with H2O is on account of formation of intermolecular hydrogen bonding between H2O and ROH. So if I see that the solvent is capable of forming intermolecular H bonding with the solute particles, then the solubility in the particular solvent will increase because of the ability of forming intermolecular hydrogen bonding. Now, it may be noted that hydrogen bonding also influences other physical properties, viscosity, surface tension, like this. Okay, so this is glycerol. It has 3 OH. Ethanol has 1 OH. The hydrogen bonding is more extensive in glycerol because there are more number of OH atoms than ethanol. So glycerol is more viscous than ethanol. If anyone is asking you why glycerol is more viscous than ethanol. Okay, viscosity is also affected by the extent of hydrogen bonding. Now in the introduction part, I have told you there are 2 types of hydrogen bond. One is intermolecular and the other is intramolecular. Intermolecular hydrogen bonding exists between different molecules having same structure, or rather of the same substance, like in HF, like in NH3, like in H2O. These are intermolecular hydrogen bonding, also like in alcohol and water. So previously, like HF or in H2O or in NH3, there were hydrogen bonding existing between one HF to the other HF unit. But in case of alcohol and water, it is hydrogen bonding existing between ROH to that of HOH. Okay, to that of HOH. So let us not forget that physical properties are what? Melting point and boiling point, and that is affected by the extent of hydrogen bonding that is formed between one entity to the other entity. Next is intramolecular hydrogen bonding that exists. I gave you one example like O-nitrophenol. Now we can see it is formed between hydrogen atom and highly electronegative atoms like fluorine, oxygen, nitrogen, present in different bonds but within the same molecule. So within the same molecule, that type of interaction will exist. for which there occurs cyclization in the molecule, and it prevents their association, rather I will say. So it prevents their association. So this is it. Now a few examples are O-nitrophenol and O-nitrophenol and P-nitrophenol. Here we can see intramolecular existing between O-nitrophenol and O-nitrobenzoic acid. You know, there is a question out of O-nitrophenol and P-nitrophenol, which is more steam volatile and why? So O-nitrophenol is steam volatile, or rather I will say more steam volatile than that of P-nitrophenol, because P-nitrophenol forms intermolecular hydrogen bonding. It forms intermolecular H bonding, for which it actually forms associated molecules. It forms associated molecules. So we can show that in this manner, like NO2 and OH. Suppose I am drawing the structure of P-nitrophenol. P means para-nitrophenol. So this is one OH, and suppose this is having hydrogen bonding, and to the para position there is nitro, N double bonded O, and a covalent bond O. Covalent bond O can be a positive and negative. This can be hydrogen bonded to another OH of another unit of P-nitrophenol, and like this it goes on and on. It's a complete association that takes place, complete and continuous association that goes on and on wherever there is oxygen, wherever there is hydrogen existing between one molecule to the other molecule. So this is known as intermolecular hydrogen bonding, forming associated molecules, and so the energy required to break those associations are higher. So the boiling point is also high, and the intramolecular hydrogen bonding existing in O-nitrophenol makes it more steam volatile. These are certain revision questions. See, this is the question that we have discussed. Now, sucrose is covalent molecule. It is quite soluble in water. Explain why. So you research about these questions whose answers and indications I have already provided. So as of now, thank you all of you. I will try to give some more shots and videos on the practice questions related to this chapter.